Thank you for coming. Okay, we're good. So before I get started here, I just want to get an idea of my audience. So a quick show of hands. Who here works with Terraform on a regular basis? Okay, about half. All right, and the other half, I assume you've at least used it, or you might not be here. Okay, so I'm Kyle. I work extensively with infrastructure as code for multiple different cloud providers. I am an active contributor to Terraform and the Terraform Registry and a lot of modules that are on there. I did my PhD at the Massachusetts Institute of Technology in the Computer Science and Artificial Intelligence Lab, which is this wonky-looking building here. Although as weird as it looks, some very interesting stuff does go on in there. And after that, I started my own company, Invicton Labs, specializing in cloud infrastructure, IoT, kind of custom electronics, and all that sort of stuff. And today I'm going to talk to you about supply chain attacks. I think most people nowadays are at least familiar kind of with how these things work. But a quick recap, what is it? Supply chain attack is when an attacker injects something malicious into a trusted third-party source that you are using, or a dependency, we might call it. And the victim then uses that without verifying it first. So it gets injected into their system and then runs on their machines. And this allows the attacker to have access to the victim's systems or the victim's users, depending on how the attack is done. This can happen with both open and closed source projects. And we're going to go over a couple examples to really see how that's happened in recent years and some significant events. So you may have heard of one called the SolarWinds attack. This was a pretty interesting attack that was very large in scale, affected 18,000 different customers, including a number of departments of the US government. And it was a sophisticated attack that went on for quite a few months before it was discovered, which is one of the reasons it was so harmful. It was attributed to a group called APT29, Advanced Persistent Threat, just a code name that various groups give them, also known as Cozy Bear because we think they're Russian. And it was really one of the first attacks to highlight just how severe this was in terms of global supply chain of software and how many different entities use some of these packages. So let's look at what actually happened in this attack here. So first off, September 4th of 2019, the attackers were able to gain access to the build system for a piece of software called Orion. We're not 100% sure how that happened, but most likely it was through a compromised Microsoft account. Over the next few months, they managed to inject a little strip of a proof of concept into some of the code, into the build system, to prove that they were able to modify the final build that got released out to customers. That succeeded, and so in February of 2020, they actually did that attack. They had their malicious code, and they built it into a production release of the software. Over the next few months, over 18,000 private organizations and governments received that malicious code that was released. And it was about 10 months later that a company called FireEye, now known as Mandiant, announced that they had been hacked. And this was traced back to the SolarWinds software. So Mandiant was a customer of SolarWinds and was affected by this malicious code. So 10 months of this being an active breach and data being stolen. They did it in a fairly clever way by using the build system, as I mentioned. So they gained access to that system and an account that was able to modify the build system using a compromised account, and they injected a script into that system that did a couple things. First, it waited for a specific DLL, because there's a Windows software, to be compiled. And once that file was created, it then renamed it to some temporary file name. It wrote a malicious DLL file with the same name, but with a little extra code added to it. So it took the compiled code, added a little extra malicious code, and then put it under the same file name. The build system then went and packaged all of that together into a release and signed it. Right? So they had code signing, but what they signed was malicious. And then after that, it deleted the malicious DLL and renamed the original one back to its proper file name so that anyone going through the artifacts would see the proper one and not the malicious one. So then, like I mentioned, this distributed package was actually signed by SolarWinds, so anyone doing code verification would see, yep, this has a valid signature, we should be able to trust this. Because it was closed source, no one was able to actually look at the code and see if anything had gone wrong. It was the craziest thing I had ever seen. So CrowdStrike was one of the companies that was hired to investigate this and dig into it, because this was kind of a new attack that no one had seen before. And the impacts were pretty significant. Class action lawsuit against SolarWinds for $26 million. Tens of millions of dollars on top of that for the investigation and the recovery and dealing with the problem. US Treasury, State, Energy, and Homeland Security, some of the most important departments of the US government, were all compromised by this. 100 private sector companies, including some very big names that you've definitely heard of. And they think it was carried out by a Russian-backed group that had support of the Kremlin. Kremlin denies any involvement. Absolutely shocked about that. So that example of one significant attack. Let's take a look at another, NotPetya. This one was pretty interesting because of the scale of it and the scope of the impact of it. So Russian attack targeting Ukraine in 2017, so after they invaded Crimea, before the current war. And it was considered one of the most destructive and costly attacks in history. It affected companies all over the world and caused more than $10 billion in damage, some of them being like the largest shipping companies in the world. And it was done using this archaic piece of accounting software called MEDoc that a lot of these companies used, particularly in Ukraine, which is why it was targeted. And there was an update server for this piece of software that would remotely fetch updates and then install them. And they were able to compromise the update server. So the update was obviously not a real update, but instead they pushed some malware onto these computers running this old software. And they managed to use a couple exploits that were known in Windows at the time, but that they had not patched in their machines. The first one called Eternal Blue, which allowed remotely running code on remote machines, and then one called Mimikatz, which allowed extracting passwords from memory that were stored there. And so they were able to remotely execute code that retrieved the passwords, and then they reset those passwords to be able to give themselves remote access. And they used, so a lot of computers on the networks were patched, but because there were some that were unpatched, they could extract a person's like Active Directory password from there and then use it against any other computer. And that is why it spread so quickly. After that, they encrypted the master boot record. It wasn't ransomware. They didn't ask for money to try to decrypt it. They were just trying to cause damage. So they encrypted the MBRs and then bailed, and that spread across the world. The cost of this one was also pretty significant, $10 billion estimated. Part of the reason we think they did it was because by causing this massive amount of damage, it served as an excellent distraction for other cybercrime that may have been committed on those machines or at the same time. And they would have been aware of what kind of collateral damage this caused by encrypting the MBRs of thousands of computers, but they just didn't care. And that kind of shows to go what you're up against when you're talking about state actors and government-funded groups that really just want to cause havoc. Let's look at some open source ones, because you say, well, those are all closed source, no one could inspect the code, so of course that's going to happen. Well, it happens in open source too. This one's one of my favorites just because of how ingenious the approach was. So Utils is a compression library that is included in almost every Linux distribution. And the attackers here spent 3 years preparing for this attack. The malicious version that was compiled and released was included in several development Linux builds, so like release candidates, and was just about to go out into a production release when it was caught. So the way it worked is it used the SSH daemon to get system access, because in many systems, SSHD is linked to systemd, and systemd is linked to the lib LZMA, which is the Utils library. And so by using a dependency, they were able to get into some of the larger programs that were running. Debian and Red Hat, very close to releasing to production before it was caught. It was discovered almost as a fluke when a researcher was using this new software, testing it out, making sure everything worked well, and noticed that their computer was running a little sluggishly, that things weren't as snappy as they should be. So he started digging into where those cycles were going and what was, why the software was running so slow. And when looking through the code and what had changed in a recent release, he found this and alerted the community, and that got pulled out very quickly. So the way it worked was more of a social engineering than anything else. We have a GitHub user, GiaT25, who spent 2 years meaningfully contributing to this software. So this user pushed real updates, valid pull requests, made feature changes and implementations, and was just generally a great person all around, a great member of the community. And they obtained the trust of the repository maintainers. Around 2 years after that person started doing that, when they had that trust and were a name that was known in that group, all of a sudden a bunch of users started popping up on the email list who hadn't been seen before. And these users started complaining that, hey, these maintainers are not very active. They should really hand the reins over to someone else. You know, let's keep this going a little faster. Let's give access to someone who has a bit more interest in contributing. And they started pressuring those maintainers, and the maintainers said, okay, fine, well, we'll give it to Gia then because this person has been contributing, a good person, valid member of the community, et cetera, et cetera. And once Gia had those permissions, they implemented malicious changes to the build system. Now, what they did was not obvious. They, and this is where I think it really gets ingenious, is instead of pushing malicious code that anyone could have seen, this library, because it's a compression library, has a bunch of test files with it that are just binary data of various sorts, and they use these test files to test and benchmark the compression ratios and performances. And so what Gia did was they took some malicious code and obfuscated it and then masked it as one of these binary test files. And then in the build system, they de-obfuscated that code out of the test file and then injected it into the release. And because of this, anyone looking at the open source code would not have seen anything. Now, anyone doing a checksum would have found the difference, but not a lot of people do that, if we're being honest. So this overall is a rapidly increasing threat. We're seeing a pretty quick increase in the rate of these attacks occurring. And this, I think, is probably because there are just so many dependencies that we use nowadays. Your average project has 203 dependencies, and that's from a survey a couple years ago, so it's probably higher now. And 45% of those same survey respondents did experience a supply chain attack of some sort back in 2021. Again, that's almost certainly higher now. And of those victims, more than half of them did not have any strategy ready to respond to that or way to deal with that. They had no way to detect it, no way to recover from it, or no backups to deal with ransomware or other issues. So let's look at how this actually plays out and why it's such a big problem. To investigate this, I went to PyPy and found the most popular package, which is Bodo 3. If anyone here works with AWS, you'll recognize that. That's Amazon's SDK for AWS. It has 1.3 billion downloads per month, roughly. Very widely used package. It has 3 dependencies, Bodo Core, S3 Transfer, and JMES Path. Each of those has a bunch of dependencies. Each of those has a bunch of dependencies. And we start getting really, really deep several levels down here, and we see some interesting things. We have over 2,700 contributors across these, and close to 15,000 closed pull requests across these. Realistically, who is looking at 15,000 pull requests? Who is evaluating hundreds of thousands or millions of lines of code when they're releasing something like Bodo 3? And then you start seeing things like this. So enum34 here. I dug into this. I tried to find the source code. I could not find a username of who authored this. Parse type has one contributor to it named Genesis. One contributor, that means likely no one has evaluated this code, no one has reviewed it, no one is looking at these PRs to approve them, which means that this person's code that in many cases has not been reviewed has ended up in Bodo 3, the most popular package in Python. So this kind of gives you an idea of the sense of scope of this and just how difficult it is to really trace these issues and make sure that the dependencies you're using are actually safe. And on the topic of open versus closed source, it can really go either way. There are benefits and drawbacks to each, and that with open source, obviously anyone can contribute. So you have things like Gia T25 going in there, and as a new contributor, we're going to allow them to do that. You have no vetting of those maintainers like we saw in that case. On the closed source side, though, no one can review the security of the code. So you get an update, it's a binary that's signed by the company. You have no way to go in there and see what it's actually doing. And you have fewer people looking at it who might be able to catch it. On both cases, you'll have inexperienced developers who might be doing insecure things. But on the open source side particularly, you do not have control over the dependencies of your dependencies. Unless you're going and recursively cloning everything and forking it and building your own dependency tree, you cannot really control that. So now we're going to do a live demo here, which is what I'm sure you're all here to see. And I'm going to show you just how easy this is to pull off. So we're going to start with a module called null assertion under the null provider. Now this is based off of a module that I published many years ago and have kept up to date since then. That is one of the most popular modules on the Terraform registry. So 60,000 downloads per week, 5.7 million of all time. So this is, my estimate is with 60,000 downloads per week, I think there's probably 500-ish companies using this, is my guess, based on how often companies apply Terraform changes and such, or reinitialize and re-download new modules. So 500 decently sized companies is kind of the estimate I'm going with. It's just a ballpark that I'm pulling out of the air. But what I've done is I've cloned this module and republished it under another username called Please Don't Ban Me, because I do not want this associated with my real account on Terraform. But essentially, all it does, it's very straightforward. It just does an assertion that something is true, and if that is not true, it throws an error message and then kills Terraform. Because this is something that Terraform doesn't really have built in. You can do it with variable assertions, but you can't do it with other conditions. And really, that's what this is doing. It's kind of wrapping this in a variable assertion. And we can see that here, not here, here, where it's just asserting that the condition is true, and if not, using that custom error message. Now, before current Terraform versions that allowed you to do these validations of variables and referencing other variables for the error messages and such, I did this in a much more complex way, so now I've simplified it. But overall, this is essentially all the module does, and it just wraps it in a pretty format. So I've republished this under another name, and it is here on the Terraform registry. That's it. That's all it does. And now I'm going to have a Terraform configuration here. So we're going to do this using Azure just because this is a Microsoft-ish kind of conference. And all it's doing is it's saying that, are you logged into the tenant that we expect you to be logged into? And it's asserting that the current tenant ID equals the expected tenant ID. And if not, it throws an error saying you're using the wrong tenant. That's it. That's all this thing does. So I'm going to clone that repository. Let's look at what we're using for Terraform here. I think I'm a couple versions. I'm on 11.3 here, not too out of date. And we're going to do a Terraform init. Oh, no, I'm going to cd into the directory first. To my victim Azure directory. Terraform init. Can we see this? Is this big enough? Kind of. Okay, and we'll do a Terraform plan. I'm not going to actually change anything. And no changes, no issues. Everything's happy. So it read that data source. It found that the tenant ID that I'm currently logged into with Azure does match the expected one. So the assertion passes, and everyone's happy. So the other thing I want to note is, because you are all Terraform experts, if anyone sees me do something that seems unrealistic or contrived for this example, I want you to speak up and tell me I'm doing something wrong, because I don't want to be caught manipulating this in an unfair way. Any problems so far? No, this all seems legit. Okay. So now what I'm going to do is I'm going to go here where I've published this module, and I'm going to delete this version of the module. Remember that the publishing is under the attacker's side of this, right? The attacker manages this module and has a malicious module, so the attacker is able to do this. We'll delete that. And now I'm going to go to my assertion here. I'm going to go and I'm going to delete that release. And we'll delete the tag that went with it. And this time what I'm going to do is I'm going to use the same tag name, 040, except this time I'm going to target not the main branch, but the malicious branch. I'm going to publish that. And we're going to go back here. We're going to refresh this. We'll see we're back to 4.0, but this showed up all of a sudden, which is interesting. OK, now for this demo to work, two conditions must be met. The first is that it must be a clean initialization of Terraform. So that can happen in many different ways. If you have a new developer who's working on it, they're going to do a Terraform init when they're doing it locally, and they're, for the first time. If you're using an automated deployment process that has a new virtual machine every time it spins up, that'll be a fresh Terraform init. I think Terraform Cloud, if you do it there, actually does a fresh init every time. So this is not an uncommon condition to meet, I'd say. The second condition is that we either have to wait 2 weeks from now, or I have to bump the version of Terraform. Can I get any guesses from the audience of why one of those two must be met? I have no courageous members up here. OK. So what if I said that the Terraform registry uses AWS CloudFront as its CDN with a 2-week cache timer on it? And when I query the path for a module, it includes the Terraform version as a header. So by bumping the Terraform version, I am essentially doing a miss on the cache, and it's fetching from the origin instead of giving me a cached result. So that is why I either need to wait 2 weeks for that timer to expire or do a version bump. Now, of course, either of these could happen. It is not unrealistic that 2 weeks from now, someone's going to do a fresh Terraform init. And it is also not unrealistic that someone's going to update to the newest version of Terraform each time it comes out, given that it throws an angry message at you if you don't. So I think that is also not an uncommon condition. So I'm going to upgrade from 11.3 to 11.4. And to simulate a fresh initialization, I'm just going to straight up delete this repository as if I was just working on a new machine here. And we'll do the same get clone again. And we'll also look at our Terraform version. And we'll make sure, yeah, now I'm using 11.4. OK, that's good. So let's go back to that same directory. No concerns? OK, speak now or forever hold your peace. And we'll do our Terraform init. OK, and we'll do a plan again. Note, I'm just doing a plan, not an apply of anything here. Because remember, a plan does not require you to confirm anything. You don't have to type yes for it to happen. OK, so that's happened, and no one's raised any objections so far. And now I can tell you the attack is complete. It's done. We have what we need. So if we look at what actually happened here, not AWS, in Azure, we'll see that in this Terraform directory where it cloned the modules, we have our assertion module. And in here, we have a whole bunch of files that weren't in our initial initialization, like these PowerScript and shell files here that do some interesting things. So these are scripts that I've written that in the malicious code, if I can find it here, under attack.tf, we are running an external data source that is calling these scripts. And you might note that on some machines, it does not allow remote script execution. If you've downloaded a script off the internet, particularly on Windows, PowerShell will not let you execute it. But we have actually circumvented that by using Terraform to load the script from a file, read it from a file, and then write it to the file system, which makes Windows think that it was a locally created script instead of something that was downloaded off the internet, which allows me to execute it without throwing any warnings. And then if we actually look at what the script is doing, we are starting this as a separate process that runs in the background. So Because this takes a little while for what it's doing, we start it as a separate process and then return a valid exit code, and Terraform is fine with that. It thinks that whatever I was trying to do completed, it got an empty data set back from that external data source and completed its execution while the script was still running in the background. And now what I'm doing is, and you can review this code, it's all on GitHub if you want, but in a nutshell, I am getting a bunch of sensitive information. We'll scroll down to here. So I'm getting all of my environment variables, which if you're using Terraform might have something sensitive, like an access key to something. I am getting all of the files that are in certain directories, in this case .ssh. Perhaps there's something secret or private in that file, in that folder. And then what I'm doing is I'm checking if the Azure CLI is installed. If you're following guidelines properly, or the way that it recommends it, and you're using Terraform with the Azure provider, you almost certainly have the Azure CLI installed, because that is how you do an SSO login so that you can execute Terraform locally without needing long-lived credentials like an access key. We can also see if the AWS CLI is installed, which if you're working with Amazon, it almost certainly will be again. And what we're doing here is we are using these CLIs to go through and see if there are any active sessions. So because I logged into Azure, I did it before we started because I don't have time to go through all that stuff as part of the talk, but I just did an AZ login, and I logged into Azure on the CLI so that I would be able to run that Azure data source to get the tenant ID. Something you'd have to do regardless of what cloud provider you want to use. With Terraform, you have to do a login if you're using SSO with it. And say I did the same with AWS. And then what I can do here is I can actually use those CLIs to spit out the current session keys. Right? So if you're using AWS SSO, for example, it will generate a session name and a session token that essentially act as an access key, even though they're short-lived, only a couple minutes usually, or maybe an hour or so, depending on how you have it configured. They're still no different than a permanent access key in terms of the permissions that it gives me. And the other thing is that when you're using Terraform to manage large infrastructures, most of the time you're going to have administrator level credentials or access on it, because that's the only way you can deploy and manage a lot of this infrastructure. So what I've done is I've grabbed those session keys that have administrator level access, and then I'm doing some funky encoding. I'm base64 encoding it, and then I'm encrypting it with a public key. The reason I'm encrypting it is so that if anyone's looking at the network logs and they see this egress traffic, they have no idea what I have egressed, right? So they know that something has exited, but they have no idea what it is because it's encrypted with a private public key, and only I have the private key for it. And then what I'm doing is, and this I thought was fairly clever, so a lot of times you'll find that exfiltration of data happens with something like DNS requests, because those are fairly easy to do, because in most cases public DNS is available even in private networks, but not all the time. A lot of the entities I've worked with are pretty locked down and don't allow that. They only allow private DNS, so that doesn't work. So I asked myself, if I'm using Azure, what public endpoint would be available, almost guaranteed? And I realized that Microsoft uses the same login URL for every tenant. Or sorry, the same login domain for every tenant, which means that that domain in general is going to be whitelisted. And the IPs associated with it, therefore, will be whitelisted for public egress. And so what I've done is I've created an Azure tenant of my own as the attacker, and I have made login attempts into that tenant using this login endpoint. And in my user agent field, down here somewhere, I am putting parts of that payload that I want to exfiltrate out of this victim system. And so it's sending that data as part of the login request. So that means that now, when I go into my Azure, this is the attacker's Azure, and I look at my sign-in logs, and this takes a while because it's horrifically slow. Still not there yet. And we'll see, there we go. So these two up top here, these three up top, are attackers. So this is the user that I'm trying to log in with. It's not a real password that I'm sending, but it logs the attempt. And if we look at the logs, we'll see that down here in this user agent field, we have this cool base64 encoded encrypted value, which now, as the attacker, I can download. So let's download those. And we will now go to the attacker's side of things. So I have this funky little Python script that just basically undoes everything I did in the PowerShell script with the encryption and the encoding and so on. So it loads this JSON log file and extracts the payloads, puts them in the right order, decrypts them, decodes them, and reassembles everything. So a couple interesting things to note here. One is so it found 2 entries. One is the one I just did, and one was from testing earlier this morning to make sure HashiCorp didn't patch this issue before my talk. But it found that the token was valid. So it actually used that token that I exfiltrated, which, like I said, in most cases would have admin permissions, and used it to make a request against the Azure API to confirm that it was a valid token. And I just used a simple get tenant information endpoint as an example, but it does get all that sensitive information, right? It has my tenant ID, country, like anything else I want. And with this token, I could make requests against any API endpoint for Azure that I want. I also extracted all those environment variables, as we can see here. So these are all the environment variables that were running on the victim system. And everything that was in that juicy.ssh folder I now have, like this one. Should I click it and show you? It's fake. But it did come from my system. Because if we look here, let me see. That seems to be exactly what I have on my file system. So I exfiltrated this private value, and even though that file is locked down with all the the 600 permissions that you'd normally have on a private file, I was still able to exfiltrate it because I ran it as the user who owns the key. So that's the attack, right? It's that easy. And this comes down to a major flaw with HashiCorp and their system. And we'll kind of talk about that a little bit here. Oh, yeah, so Chekhov. So after I gave this talk another time, someone asked, well, what if you just use a tool that would validate your config and make sure you're not doing anything wrong? And that's an excellent question that I had not actually tried. So let's do that and see, would that save us? I don't know why it's so slow. It's a pretty simple program. Okay, well, while that's running, let's look at a couple interesting things here. So, first off, how Terraform actually loads values from the Terraform registry. It's just doing a GET request against that CloudFront CDN that I mentioned. And we can see that it is using that header, the Terraform version header that I mentioned, which is how I'm able to circumvent the cache after I publish the malicious version. Another question that came up was, what about OpenTofu? Are they doing it any better? Are they doing anything more secure? No, they're doing the same thing. They're just doing a GET request, or a GET request against the Git repository. And it doesn't actually maintain the commit hash or anything to ensure that this attack doesn't happen. So both of those problematic. I also want to show you this. This was back from 2018, issue that is still open many years later that documents this exact issue, right? There's a risk that if the registry is compromised, it can serve out a malicious version for this version number. So this is a little different. Originally, the registry didn't use commit hashes at all. It only used tag names when it pulled things from GitHub in the back end. And then they pushed an update that said when you publish a module version, it takes the commit hash of that and stores it in Terraform's database so that when you make a request to pull a module, it always gets the same commit hash. And that way, if the code changes, well, it doesn't matter because it's referencing the commit hash. But what they didn't do is consider that an attacker might just delete the module and then republish it under the same name, which deletes it from their database and circumvents that check. So this issue's been open for 7 years now, over 7 years, and they're aware of it and haven't done anything. Let's see if this completed. There we go. So, okay, it is upset. It has failed to check. Ensure Terraform module sources use a commit hash. That is an excellent point. So when we're using modules in Terraform, that's the attacker. This is how Terraform recommends you do it, because they want you to use their registry and they want you to use version numbers like this. And they want versions to automatically update so you can do things like pinning to minor version but allowing new patch versions and things like that. You can also do it with a commit hash, right? So you don't have to use the registry at all. You can instead use a get URL with a specific ref hash on it. And this ensures that it can never change. So this does effectively prevent the attack that I just mentioned. And by doing so, you circumvent the registry, which has pros and cons, but you're not subject to this issue. So let's say I do that. I make that change. Now what I've done here, so this module that I'm referencing is simply a module that wraps what I just did. So if I go, I'll show you. So this is that module there, and it's doing exactly what was in my initial config, right? It's getting the Azure tenant ID, and it's doing that assertion to confirm that the tenant ID matches the expected value, which in this case is given as a variable. So it's just a wrapper for these two things, or these three things up here. So if I do that and I run checkoff again, it's happy because that problem no longer exists, right? Now I'm using a commit hash. But as I just showed you, so this is referencing this commit, and this commit internally is using the Terraform registry. And so even though you're using a specific version of a module, if that module internally uses the Terraform registry, you are subject to exactly the same attack. So in order to do this, and if you want to use open source modules, you will have to recursively fork every single one of them all the way to the bottom and change any references to the registry to be specific commit references. And I will tell you that most modules out there use other modules internally, especially all the popular ones like the Terraform community or the Terraform AWS community ones and the Cloud Posse ones. Those are all often use their own modules internally using the Terraform registry. Okay, so checkoff does not save us. Now, in terms of, is it morally appropriate for me to demonstrate this all and to show the world, because this is being recorded and published, that this attack is possible? Because there are people out there who control those Terraform modules, like myself, who have not been vetted by anyone, right? Like when I published that module 6 years ago now, nobody knew who I was. My name had never been heard in the Terraform community, and yet it has 6 million downloads. And that can be anyone, right? Anyone can do that on the registry. So I wrote to HashiCorp, to their security@hashicorp.com, which is listed on the CVE registry, requesting that they publish a CVE for this. And I went through and I documented all the exact steps you needed to do to reproduce this. And they responded saying, thank you, we only do this for our other software when there's a specific action people need to take to mitigate, blah, 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 blah. But we'll look into it. So they refused to issue a CV and said they would look into it. That was in June of last year, so almost exactly a year ago, and they have not fixed it, as I just demonstrated to you. And if you've ever tried to get a CVE created for something you've discovered, you'll know that you don't actually have a lot of say over this. Because if you look at these steps, you discover it, you report it to the CVE program partner. In this case, HashiCorp is the partner because they are registered as a partner and it's their software. So you report it to them, and then they assign a CVE ID. If they refuse to do that, there's not much you can do about it other than try to publish it to the world like I am right now as much as you can. So that's the attack. Now let's talk about what you do about these kinds of things, because this is specific to Terraform, but the concept of supply chain attacks, as hopefully you now recognize, is very broad and very serious. So when we talk about risk of an attack, it's a factor of probability and impact, the chance that it's going to happen and the impact if it does happen. So obviously we can reduce our probability, or we can reduce our impact, or hopefully both. To reduce your probability, you have a number of approaches you can take to this, right? First, you can fork those important dependencies and make sure that nothing changes, make sure that internally they're referencing static references that can't change, unlike the Terraform registry. And you can avoid unnecessary dependencies wherever possible, right? If you are not using a dependency, use a tool that goes through and finds that and remove it from your log file, remove it from your package or from your software altogether, because it's just another attack surface. When you are using dependencies, use a commit hash. Now, a lot of languages do this already with lock files, but when you do that, and if you do a version upgrade or something, it's just going to automatically use the hash of the newest version. And unless you're going through and actually looking at the commit changes and seeing what someone has done, that's still a very easy avenue for attack. What about preferring trusted vendors? Yes, it helps. Particularly open source trusted vendors are a pretty good option. So for example, the Terraform AWS or Azure providers are managed by HashiCorp, and they're still open source. So you get the benefits of it being a preferred vendor with limited contributors while also being open source, so you can see what it's actually doing. That is preferred where possible, but obviously not always going to be the case. And we can also minimize the impact. So the principle of least privilege, or the minimum permissions model, which hopefully everyone here is using whenever they can, but we want to do a couple things to minimize the impact, right? If you're running installed software, running it as a dedicated user with strictly limited permissions, this is standard practice in most Linux software that is risky. Or if you're using things like Nginx, for example, you usually run it as a designated user with limited permissions. Windows, it's less common to see that happen, but you can still do it. And you never want to grant your automated software admin permissions, because if you get a malicious patch pulled in, it will destroy everything. When it comes to cloud tools, everything being role-based access, always minimizing the scope of those roles as small as possible. That used to be pretty hard, but nowadays with tools like Amazon's IAM policy simulator and things like that, you can actually pretty easily say, I want to do these things. What is the minimum scope of permissions needed to do this? And making sure that your roles are actually limited to those. And also making very strict policies about who can assume those roles. So we often see, someone will create a very strict role, and what it can do is limited, but the assume role policy, or who's allowed to assume that, would be limited to, or would allow an entire Amazon account to assume it instead of a specific service or a specific region, or really narrowing that down as much as possible. And always giving them read-only permissions whenever that's viable. Network segmentation, still, we're talking many decades old best practice here, but still a great idea. Keeping things in different subnets and using security groups and ACLs and other tools for restricting what can communicate with what. When we look at the SolarWinds attack, we found that quite a few customers who got that malicious software, the ones who were not severely impacted were the ones who had these controls in place, and that software could not egress out to the attacker's servers. So it couldn't make any outbound connection, which prevented inbound connections over that as a reverse tunnel. Playing detective. So looking at what is going on with your tools. So always monitoring your traffic. Lots of automated tools available these days that are drastically coming down in cost. And we can monitor our traffic logs, looking for really odd behavior when it comes to logins, people assuming roles. Why is Bob, who usually works a 9 to 5, assuming his role at 1 a.m.? That doesn't seem right. Maybe let's flag and block that until we can verify it, or do 2FA or something else. And being really careful with the automatic updates. As we saw with the NotPetya attack, anything that updates itself without human intervention or permission can be highly risky. And really looking into abnormalities, right? So why is something running slower than it should be? We saw that with the XZ Utils attack. Someone discovered that because they really dug into, why is my SSH daemon running so slow? Or why are we making outbound connections to a new endpoint that has never been, or a new domain that has never been queried before? Or What is this software running, this process running that has a name that has not been whitelisted and has never been seen before? So all these kinds of abnormalities are great red flags about something happening that are pretty easy to pick up on and immediately block until you can verify it. Multi-factor authentication, still by far the best way to block 90 to 98% of attacks. Malware can steal passwords, but it can't steal your hardware keys. That's kind of the whole idea behind it and behind FIDO2. So anywhere you can, when it comes to SSO, being able to log in as a user, this is a very important approach. For the Terraform registry specifically, because that's what we're talking about, there's not a lot you could do about it. You can fork the modules and you can change the references inside of them to make sure that it meets those strict hash locking that I talked about by pinning it to the hash. Or you can use a module that I built specifically for this. I asked myself, how would I do this in a way that doesn't cause me to have to recursively go through and fork all these dependencies and still be able to use open source modules? So I created a module called called Terraform Module Lock. So what's interesting here is Terraform has a provider lock file that will make sure that the providers, this can't happen with the providers because it has a lock file that has a commit hash and you can't update that without being aware of it. In their documentation, they even specifically say, we only do this for providers, we don't do this for modules. They don't say why they don't do it for modules, but they don't. So I said, can I just replicate this with a module of my own that creates a module lock file? And that's exactly what this does. So when it first runs, it will go through and check if there's a lock file. If not, it'll basically generate a checksum of all the files in all the modules that have been cloned and lock each of those modules to that check file and write that into a lock file in your repository. And then on every subsequent run, it'll do the same thing and compare that hash or that checksum with the one in the lock file. And if it doesn't match, it will kill Terraform. The same with the assertion module works, and exit with an error code saying this module has changed and you're not aware of it. So that works pretty well. If you want to test it, please, I could use some more feedback on it. I think it's a pretty cool tool to deal with this until HashiCorp finally fixes their stuff. So with that, that concludes my talk. Thank you very much for your time, and I'm happy to take any questions on this or anything related.